Okay, so today we are starting with correlation. So a lot of the stuff that we're going to be talking about for the next few classes is very different from what we've talked about before. So it's different than ANOVAs, it's different than t-tests. So if you didn't understand t-tests and ANOVAs really well, that shouldn't affect your ability to learn this pretty well. That said, there are some relationships between t-tests and f-tests to correlation. So let's do a quick review on the two types of tests that we've done so far. Did anyone categorize the two types of tests for me? What types of tests have we done? We've done t-tests and f-tests. Well, that's two types, but someone also said z-tests. Well, that's three types. We also did binomial tests. That's four types. Is there anything that you can group those things into? Say there are two types?
Normal and normal distribution.
We could group them into tests that require an assumption about normality. That's absolutely right. So the z-test, all of our t-tests, all of our ANOVAs made this assumption that the populations that we're sampling from are normally distributed. The binomial test, we didn't assume this at all. We had a completely different distribution of binomial. That's really good. I'm proud of whoever said that. Anyway, I was thinking about types of tests a little bit differently. I was thinking about tests of being and tests of relationships. So there's this famous play written by some dude, like Bill Shakespeare or something. Some crazy yokel. It's called Hamlet. And there's this famous line, to be or not to be, right? So we have questions about being. So in English, I think some people say dude, I'd be hungry right now. Or I'd be going over there later. But typically people don't say be. They say is, right? Or am. I am a teacher. This is a class. So our tests about being are is tests. The binomial test is a test of being, where we ask, is the probability something? Right? We were hypothesizing that the probability is a test of being. We also had z-tests, which is also a test of being. What were we testing with the z-test? Yeah, we said that the mean is something, right? It's a test of being. What other test is a test of being?
T-test
What type of t-test? Because we had a whole bunch of them.
Yeah,
Independent.
One
One sample, yeah. With the one sample t-test, we also had a statement about the mean is that, right? And the other tests that we've talked about are tests of relationships. So what were the tests that we've talked about that have to do with relationships? Independent t-test. How is that a test of a relationship? It's a comparison between two means. We have two means. And I guess you could phrase it as a being question. There is no difference. Or the difference is something, right? So you could phrase it like that. But I like to think about the relationship aspect of it. Right? We talked about how we could figure out if there was a relationship between our independent variables and the dependent variables, right? Is there a relationship between the types of media that you see and your political feelings, right? This is a test of a relationship. Is there a relationship between these things? So independent t-test qualify. What else qualified? The paired t-test qualified. The paired t-test was just like the independent t-test, except we were able to get rid of some of that variability that had to do to subjects. What other tests were tests of relationships? Which ANOVAs? All of the ANOVAs. The one-way ANOVA, the factorial ANOVA, the mixed ANOVAs, the repeated measures ANOVAs, all of those were questions about relationships. For the t-tests, we just had one independent variable. For our one-way ANOVA, we also had one independent variable. But for our other ANOVAs, we had multiple independent variables. So basically, so far we have done tests of being and tests of relationships. So we are going to continue on the track of testing relationships. So before, when we were testing relationships, what we did basically was we were comparing the variability of means to the variability of some error, right? And what that error was depended on what type of test that we were talking about. Even the t-test, remember when I first started talking about the ANOVAs, and I said that the f-test is the mean square for the effect divided by the mean square for the error, and I demonstrated that this mean square for the effect was the same thing as the numerator of the t-test, because you had 1 degree of freedom when you had the t-test. So basically, for both the t-tests and the ANOVAs, we were comparing variability of means to variability of error. We're still going to be looking at variability. Variability is really, really useful. But previously, our means came from groups, right? So we had some group that had a long list and they had a short delay. And another group that had a short list and a long delay, and all the other combinations. So we had means from different groups. And the groups sometimes are arbitrarily determined. Not all groups are arbitrarily determined. Things like major. Actually, even that's sort of arbitrarily determined, right? You could talk about psychology majors, history majors, sociology majors, political science majors, international relations majors, philosophy, religion, right? There are lots of different majors that sort of form groups. But sometimes when we've talked about groups in this class, we haven't said psychology and philosophy and business and electrical engineering. What have we said? In terms of majors, group people into majors, let me say. So how do we, like when we have talked about majors in this class, like I haven't talked about all of the majors.
Psychology and non-psychology.
Yeah, I break it down into two groups, psychology and non-psychology. It's sort of arbitrary, right? I could have broken it down differently. So on the test, there was this variable called sleep. What were the two the groups that were associated with sleep? What were the different levels of sleep?
Different levels of sleep for.
No, not like slow wave sleep and REM sleep. Not that sleep. On the test, if you did stir data, you could see what was in the data frame, and there were things like incentive and breakfast, and one of those things was sleep. There were two levels of sleep.
Lack of sleep and sleeping for 6 hours or something?
Yeah, it had to do with the 6-hour cutoff. So the groups were people that slept less than 6 hours and people that slept more than 6 hours. So what could the groups have then?
8 hours.
People that got 8 hours of sleep versus people that got less than 8 hours of sleep. Well, we've got less than 8 hours and 8 hours. We can also have people that got more than 8 hours of sleep, right? So that's three groups. Could we group things differently?
People who got 3 hours, people who got 6 hours, people who got 9 hours.
So 8, 6, and 9. We'll just leave everyone else out. We could. I'd want to say like, okay, maybe less than 6, 6 to 8, 8 to 9, more than 9. Whatever. So the groups, we could have had a lot of different potential groups. We could have said 0 to 4 hours. These are people that got a lot less sleep than normal. People that got 4 to 8 hours. A little less than normal to about normal. And more than 8 hours, more than normal. Right? We don't have to break it down like this. We could say 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. I'm sorry, it should be more than 12. More than 12, right? Or we could have included 12 to 14, whatever. We also, we didn't have to work with hours. We could work with minutes. You know, how much did you sleep last night? Well, about like 2 hours. Well, can you give me better than 2 hours? Well, like 2 hours and 15 minutes. Okay, so that's 120 plus 15. So that's 135 minutes, right? So we could have groups of people that have 1 minute of sleep, 2 minutes of sleep, 3 minutes of sleep, 4 minutes of sleep, and so on and so forth. We could keep breaking it down, right? Is there a problem with this?
Yes.
What?
I mean, how can you tell if someone's step 1 or extreme?
You can experimentally manipulate this. There are sleep labs that people come in and they sleep. And they wake them up after so much time. And they can measure when they actually fall asleep based on their brain waves. So we say, okay, once they hit this stage of sleep, they get that much time, we wake them up. So we could conceivably do this. It's possible.
The 1 or less minutes sleep doesn't have very much effect on the other variables.
Hmm?
I mean, what's the difference make when someone had 7 minutes and someone had 8 minutes?
What's the difference between someone that had 7 minutes and 8 minutes? Is there a big difference? It doesn't seem like that big of a difference. 7 minutes, 8 minutes is still not very much sleep, right? That's one potential thing. Let's ask, why do we group? Why do we group things? He sort of hinted at one potential reason. It can make it easier for us. Maybe we don't think that there's a big difference between, 6 and 7 minutes of sleep. So we can sort of collapse over those things that we don't think should be that different, right? It's possible. So we have both pros and cons for grouping things. People have this natural tendency to categorize people. Türk, yabancı, right? Başarılı, başarısız. Müslüman, gavur. Right? And so people categorize things all over the place. It's a cat, that's a dog. This is a plant, that's an animal. We have almost this instinctual ability to categorize things. Because categorizing things makes things easy for us. If I can categorize someone and say, she's a female, then I have this idea in mind about how females act and how I act towards females and maybe differences between how I act in females in Turkey and how I act towards females in America. So I can use all this information to react appropriately, right? So we make categories all the time, and this is really beneficial. It also allows us to do some fairly simple hypotheses like all the means are equal when we were doing our norms, right? Or the two means were equal when we were doing our t-tests. And this makes data analysis simple. Some people don't agree with this. Some people think that the grouping maybe is sort of unnatural. So I don't completely buy this, but yeah, some people think that. Cons. For each group you add, you need more participants. Why? Degrees of freedom. So there was one question on the homework that I thought was really hard. I made it hard on purpose because I wanted to see if you got it. And I said something like, you have this many conditions, how many people, what would the minimum number of degrees of freedom be for that?
Yeah.
Right? So you had to figure out you have to have at least 1 degree of freedom, right? So, okay, if I had this many participants in each condition, then I would have this many minus the effects and everything else. That leaves me with, I don't have enough. I have to add another one, or another one. Anyway, so we need degrees of freedom to do our tests. We had degrees of freedom for our t-tests, degrees of freedom for our alphas. We're going to have degrees of freedom for our correlations too. Degrees of freedom. I know, it's everybody's favorite. Anyway, when you add more groups, you are taking away degrees of freedom from the error. And you have to have at least 1 degree of freedom in the error terms, or you can't do your tests. So if you think back to the ANOVA, you had the mean squares of the effect over the mean squares of the error. And the mean squares of the error was the sum of squares for the error over the degrees of freedom. If you had 0 degrees of freedom, now all of a sudden this is infinite, the denominator, right? And if the denominator is infinite, you never get a significant result. Ever. Yeah, maybe not get. Well, unfortunately, when you group things, you lose data. There might be differences that are important. Maybe the difference between 5 and 6 is not important, but maybe the difference between 5 and 10 is.
How will we know?
How will you know? It's a good question. You could experimentally test things to see what differences matter. Like this has to do with like effect size. Is this difference big enough for us to pick up? How many subjects would we need to pick up a difference of this? And we talked about how to do this when we were doing our t-tests. We didn't do this really well, but there are other procedures. Okay. So he said something earlier. He said the difference between 5 minutes and 6 minutes doesn't mean anything, right? So what group do you want to use?
Hours.
Hours. 1 hour versus 2 hours?
Maybe.
Okay, now 1 hour versus 2 hours. 1 hour should be different than 2 hours, right? But let's break down where we make that cutoff between 1 and 2 hours. So we have 1 hour and 59 minutes versus 1 hour and 60 minutes. That's 2 hours. We said before that a difference between 1 minute shouldn't really matter. 5 and 6 shouldn't matter. So an hour and 59 versus an hour and 60, should that matter? Probably not. So even though some of those small differences might not matter, we are getting rid of differences that do matter and ignoring some of the others. So 5 hours or 0 hours of sleep on the test was treated exactly the same as 5 hours and 59 minutes of sleep. I would guess that there's probably a big difference between 0 hours of sleep and 5 hours and 59 minutes of sleep. Okay, so let's see what we can do to get around grouping. So when we were doing our ANOVAs, we were building models like this. Our dependent variable is a function of some conditions, or some dependent variables and their interactions. And those things together describe all of the different conditions, right? So we have our dependent variable is a function of conditions. Now the conditions includes all the combinations of the different levels of the variables of interest, and we lost conditions minus 1 degree of freedom from our error. We could build other models. We don't have to say degrees of freedom is a function of conditions. We could say something else. Like what? Let's think of a simple example. Let's just imagine a one-way ANOVA where we were looking at the test scores as a function of sleep. And we broke sleep into 2 levels. Less than 6 or more than 6, right? If it's just a one-way ANOVA, all we have are the 2 conditions, right? Less than 6 hours, more than 6 hours. That's it. 2 conditions. So here we say your test score depends on whether you had less than 6 hours of sleep or more than 6 hours of sleep. Right? Could you say that differently without referring to like a particular condition? What are we interested in? What is the variable that we're interested in? It's sleep. How much sleep you got, right? So we've said something like our dependent variable is a function of the time we got sleep. But we only broke sleep up into 2 groups. We don't have to do that. Instead, we could say that test scores, yeah.
No, I mean, we can measure the no groups of sleep, just measure the sleep, and we can just make a measure of the given.
Go up to people and ask them how much sleep they got. And I don't need to throw them in any group. I'll just take their score. And I want to see, okay, you got this much sleep, you got that much sleep. Everyone got different amounts of sleep. So, like, we can't really group people together unless we start collapsing across differences, right? So, you guys are all probably expert basic model builders, I'm guessing. So, let's take a look at this. Is this familiar to all of you? I hope all of you have done this lots and lots in high school. Probably did more advanced things like x squared, or cubic functions, and hyperbolas, and all sorts of stuff. This is simple. This is ridiculously simple, right? Now, I'm not saying that y, whatever y is sleep, this y would be our dependent variable, so that would have been test scores. So, test scores is a function of sleep, and for our group, this one we had that, and for our group that got 10 minutes of sleep, we had this, and for this many, no, I can just say that y equals 2x minus 3. I can describe a line. How many pieces of information am I using to describe a line?
Two.
Basically 2. What?
X1.
Not x and y.
And then the times variable in there. Minus 3.
Minus 3 is one of them. That's the intercept.
And
And the slope. There's a slope and the intercept, right? So this 2, this is the slope that determines whether this is steep or shallow. And the intercept that determines where it crosses 0, right? So rather than saying, okay, this is a function of this group mean, and 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 that group mean, and all of our other group means, we can say that it's just a line. Right? Cool. There is a relationship between x and y. And we didn't need groups to see that there was a relationship between x and y. Right? I mean, we could group things. Say, okay, we're going to cut people off here. So all these people go into one group. So their score is about like there. And this group is about there. Oh! Right? We can throw all those people into groups. But we don't have to. We can just use the data by themselves. With this particular function, increases in x are associated with increases in y, right? As x goes up, y goes up. And what piece of this tells us that? The slope, this 2 right here. Right? X and y, if we think about it differently, they vary together. Right? There's variability in x. We have some small x values. We have some large x values. We also have variability in y, right? We have some small y values and some large y values. And the way that these things vary, they vary together. Small values of x go to small values of y and vice versa. Right? So we have this covariation, this relationship between two things, x and y. Ooh, a correlation. What does co mean? Together with. Yeah, so if I'm the co-founder of Ulke, that means, thank you. All right, so if I'm the co-founder of Ulke, that means I'm going to get a lot of free chocolate today. It also means, you didn't see the Ulke display up front? Okay. So, it also means that I founded the company with real patron, right? I founded it with him. Did it together. So So we've got co, with, and relation. A relation is a relation. It is, but that's a bad definition. You don't want to define a word with the same word.
Not that much.
It's a word that describes.
Oh, who said that? Who said connection? Mashallah. Yes. Connection. There's a connection, a relation. So, like, I don't know the Turkish equivalent, but in America we say like, okay, I married my wife, now we're related. Right? And relatives, they're people that you have connections with. So, what happens is like having a connection with something. What? There's an effect, which means so let's talk about the effect of marriage on living, and on the place that you live. So I am married to my wife. She is an American, and people always ask me, "Is she Turkmen?" So they want to know if she's Turkish because they don't understand why I'm here. I don't know why I wouldn't be here. Turkey's freaking awesome. Anyway, so I came to Turkey. What happened?
Your wife came to Turkey.
My wife came to Turkey. Our variations in terms of place, like, we varied together. We're not exactly at the same place. She's at home right now probably, and I'm here, but like, we're kind of close. And occasionally, like, I go to a conference and she's far away, but then we come back together. If she goes on a vacation, I usually go on the vacation too, right? We vary, our position varies together. And more than our position varies together, our moods vary together. If I'm in a bad mood, she's probably going to be in a bad mood. Or at least in a worse mood. If she's in a bad mood, I'm probably going to be in a bad mood, or at least a worse mood, right? So these things are varying together. Okay, so the correlation, if we put these things together, we can have one variable's connection with another. You could say this differently. We could say the relationship between variables. The relationship between sleep and exam performance. We could also say how much variables vary with each other in relation to the most that they could vary with another. We'll hold off on this for a little bit. We'll come back. Okay, so how do we measure how much variables vary with each other? How do you do that? Does anyone have an idea?
Subtract. Find the share and see what
You can subtract something.
if we can find how many connections.
Okay, how do you measure the connection? We could observe sort of like how common the points are to one another.
There's this something represented by the dots.
Something represented by that. A scatter plot. Scatter plot. We can look at a scatter plot. Yeah. But we want to be more precise than just looking at a scatter plot and guessing. We want numbers that we can calculate. So, to do this, we're going to look at covariance. So we talked about variance. Now we're going to talk about covariance. So again, with variance is just an index of how much some variable varies. Right? Some variables vary a lot. Other variables don't vary so much. Covariance is not going to be how much a variable varies, but how much variables vary with each other. So not by themselves, but with each other. Interestingly, we can compare variance with covariance. So this is just what I said on the previous slide. So covariance is an index of how much variables vary with each other. And variance is just a special case of covariance. We've talked about special cases before, like, oh look, the t-test, that's just a special case of the f. And when you go to infinity, all of these distributions become normal. It's a special case, right? So variance is actually a special case of covariance. Variance is actually indicating how much a variable varies with itself. What? So here's the formula that you guys know for the variance, right? This is the unbiased variance. So our unbiased variance is the sum of the differences of our scores and the mean. Those things are squared, divided by n minus 1, right? So this is our unbiased variance estimate. Okay, now I'm adding in here cov XX. Cov indicates covariance. So we have the covariance of x with itself. Okay? How much x varies with itself? And I'm saying that the variations in x with itself is equal to this. So how is that? Like, that doesn't seem to make a lot of sense immediately. But if we rewrite the formula, it might make a bit more sense. So let's do that. Let's rewrite the formula. So here's the formula that we saw on the previous slide and everything that I said it equals. And here we have rewritten it. Right? So we take each score, subtract the mean from it, and we square it. Well, squaring it here, that's just multiplying it by itself. Right? And what does x minus the mean of x give you?
Difference.
It gives you a difference. It gives you a variation. This x is that different. And that's a variation on the mean. This x is differently different. That's a different variation, right? So when we break it down like this, this is not the variance, but a measure of the variability of x around its mean. With what? With itself. Okay. Whew. So how do we measure the variability of x with y?
Change. We will multiply y minus n y.
So this would be y minus the mean of y, mu of y. Let's see. The variability of x with y. So the covariance of x and y. She is absolutely right. They are absolutely right. So you have the variability of x around its mean with the variability of y around its mean. Yeah.
If you just the density first you tell us that you actually squared it because you want to distribute the zero mean to do.
Right, and we said that there are a whole bunch of different indices of variability, right? And variance was just one of the indices. We said that we could take the absolute differences and sum those up. We could take the squared differences and sum those up. We could just look at the range. You could do a box plot. The box plots give you the mean and the quartiles, right? All of those are different indices of variability, right? And we squared one particular index of variability because when we use this index of variability all by itself, something happened. What happened? So this gave you differences, which are basically variations around the mean. And if you just sum up the variations without squaring it, what happens?
You get zero.
You get zero. You get zero. So that was not a particularly useful index of variability by itself. But when we multiplied it by itself, when we put it with itself, all of a sudden we had something that was very useful. Algebraically very useful. Like you didn't have to deal with the absolute signs and a whole bunch of other nice mathematical reasons that I really don't understand, which I'm sort of embarrassed to say. But there are lots of nice properties of the variance when we did the sum of the squared deviations, where the sum of the absolute deviations would give you the same. Okay, so here we have the covariance of x and y. Like a dependent t-test, here n is the number of pairs. You have one x value, one y value. So someone said it earlier, I'm going to measure how much she slept and get her test score. I'm going to measure how much she slept and get her test score. I'm going to measure how much she slept and get her test score. I have pairs of these things. They go together, right? It wouldn't make sense for me to do something else. Okay, how much did you sleep? What was your test score? How much did you sleep? What was your test? I need that pairing to look at the relationship. Okay, even like the ANOVAs that we were doing, even when we had like a factorial non-repeated measures, we still had a pairing. Each subject's dependent variable was paired with a condition, right? We paired a condition with that dependent variable. All right, so like a dependent t-test, here we're talking about the number of pairs. Each subject has an x and a y. Okay, so let's do an example. So, okay, here are our data. 1, 2, 3, 4, 6, 8. This is going to be really bad. Okay, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, okay, 3, 8. It's okay. So we have 1 and 1, 2, 3, 4. We have 2 and 6. And we have 3 and 8. Notice these all would fit on a straight line if I could draw a straight line. Okay, so what do we need to get the covariance? What's the formula? We need to find the means. Then we need to get sample size. And we also need differences. Cool. Okay, so 1, 2, and 3. We can talk about the mean and the differences. And we can also talk about the standard deviations. We don't need this for the covariance, but we'll use it in the future. So let's just calculate those right now. Okay, so what's the mean of 1, 2, 3?
2.
Yeah, 2. What are the differences? So each of those scores minus the mean.
-1, 0, positive.
-1, 0, and positive 1. Perfect. What is the variance? From now on, when I say variance, I mean the unbiased variance. Okay? Unless I specifically say the biased, assume the unbiased. Okay. So, I'm sorry, what was it?
1.
1. How'd you figure that out?
Sum of squares.
Sum of squares. So the squares are 1, 0, 1. This equals 2. That's the sum of squares. Divide by n minus 1. 2, 1. What's the standard deviation? 1. Perfect. Okay. For y, what's the mean?
6.
6. What are the differences? -2, 0, and 2. What's the variance? 2. 4. Let's see. 2 squared is 4 plus 0 plus 4 equals 8. So that's the sum of squares divided by 2 equals 4. That's the variance. Take the square root and we get 2 for the standard deviation. Right? Sweet. Okay, now we need to get the covariance. So I'll give you the formula. There it is. So,
The mean of x is 2.
the mean of x is 2.
It's going to be 0, 0.
0, 0?
Because it's like you're not actually square root, making the square thing. So it's like -1 and 1 is 0.
-1 and 1 is 0.
Solve the first is.
Let's do variance like this. So variance was x minus the mean of x times x minus the mean of x. And the sum of all those things, right? Over n minus 1. So what we really had here was -1 times -1 plus 0 times 0 plus 1 times 1.
Yes.
Right? -1 times 1 minus 1, that's -1 squared. Right? So we just did this. 1, 0, 1. Sum those up. Divide by n minus 1. And we got the answer that we did. But here, notice that we are not multiplying this times itself. We're multiplying this times that. We are multiplying these differences by these differences. We are multiplying the pairs together. Right? Before the pairs were just the same thing. This is paired with itself. Now this is paired with something different. -1 is paired with -2. So -1 times -2 plus 0 times 0 plus 1 times 2, 2, right? So what is that? Well, this is 2 plus 0 plus 2. Divided by 2, so we have 4 over 2. This is equal to 2.
So the difference is 2?
The difference is 2, I'm sorry?
You got the difference between x and y, right?
We multiplied each difference with the other one. So this sum means for each, multiply each difference of x with the corresponding difference in y. Right, the sum, so you're going to do it for each one that you have. So multiply this one by this one, that one by this one by that one, that's that. And there you go. 2. Question? I mean, if you wanted to write so just for the variance, we had differences of 1, 0, and 1. We were multiplying by them by the differences of 1, 0, and 1. Now we have the same differences for the first part, but our second part is different. 2, 2. Okay? Yes?
What if we had 100 sample size for each group? What would we do?
If you had 100 sample size for each group, then you use R, because you already know how to use R, right? You say diffs equals x minus mean x. So we could call this diffs x, and diffs y equals y minus mean y. And then we say diffs x times diffs y. This will give us the products of those two. We'll call these products. And then all we need to do is sum products. So it doesn't matter if we have 3 or if we have 3,000. Because we have our friendly tool, R, which makes our calculations fast and efficient. All right. So, we found 2 as our covariance for x and y. Now, we brought up covariance because we wanted to talk about correlation, right? That's what this class is about. The class is about correlations. So we said that correlations are how much the variables vary with each other. That was the covariance, right? In relationship to the most they can vary with each other. Okay. This type of correlation that we're doing is called a Pearson correlation. There are other types of correlations too. If I just say correlation, you should assume that it is the correlation we're talking about today, the Pearson correlation. If you look on Wikipedia, you'll see that it's also referred to as like the Pearson product correlation, or some variation on that thing. Why do you think they'd use the word product? Well, because they're taking the differences for one and multiplying them. They're getting the product of these two sets of differences. All right. So, the correlation, just like the mean, just like the median, just like any other thing that you want to create a statistic for, there is some equivalent to it in the actual population. Right? There is some correlation in the population. Or maybe there's no correlation in the population. But there's something in the population, right?
Yeah.
So we have a population parameter. So the formula for the population parameter is this. So this thing that looks like a P is actually not a P. It's a Greek letter. Does anyone know what it stands for? Anyone good with Greek? Rho. Rho. So that's the Greek letter rho. And the correlation is the covariance of x and y divided by the standard deviations of x and y. And these are the standard deviations in the population. These are not estimates. Right? All of this is what's in the actual population. So that's a population parameter. Just like we estimated means, we estimated variance, we can estimate the correlation in the population. Yeah?
So they are already in the population, means we don't need to calculate them?
I'm sorry, what?
So we don't need to calculate them since they are in the population?
I didn't understand. Since they are in the population, you don't need to calculate the means?
Because the standard deviation thing, if they are in the population, we're provided by the population, so we don't need to calculate.
You might not know what the population mean is or the population standard deviation. You might have the entire population. I have an entire population here right now. This is not an entire population of Shahir students. It is not an entire population of Shahir students taking my psychology class. It is the population of students that are in my class right now. This is the population. Right? So I don't know what the mean age is for this. I calculated the mean for a different population before. Right? I could calculate this population mean, this population standard deviation, and everything else.
So when you said that we don't need to make estimates, you mean that we will calculate them but without the estimates?
We will need to make estimates.
You just said we don't.
If I said we don't need to make estimates, maybe, what context did I say that in? Because typically, you take a sample. You don't have the population. When you have a sample from a population, you have to estimate the population parameters. You have to. But if you have the population, this would be the formula for the correlation, the Pearson correlation for that population. If you have the population, you don't need to estimate it, you can calculate it. Right? Okay. But most of the time, we won't have access to the whole population because really I don't care about this particular set of students. Oh, that sounds so harsh. That sounds so harsh. Like if I'm interested in talking about test scores as a function of sleep, I'm not just interested in you guys, right? I care about you guys and all. But I want to be able to draw conclusions about all students, right? So I draw some sample to make estimates about some population. So we've already talked about how to get estimates of those things, right? Okay, So we've already talked about how we can get estimates of those things. So our sample estimate of the correlation, we're going to indicate the correlation with an R instead of rho. So we'll use the Greek for our population parameters like we've done before, and we'll use R here for our estimate. And now this, we are doing, yes, yeah, we are using the unbiased estimators of the population standard deviations. Also, this covariance that I taught you earlier was actually the formula for the unbiased estimate of the population covariance. We did the whole n-1 thing. If we wanted it in the population, we don't have to divide by n-1, we can just divide by n. So you know how to do both. But I taught you this one first because that's what we're going to be doing. Okay, so this last part, the most that they can vary with each other. Okay, so we said the correlation is how much variables vary with each other in relationship to the most they can vary with each other. So we have the correlation. How much the variables vary with each other, that is the
Covariance.
That's the covariance, that's this top part. So the actual covariance, that's this. How much the variables vary with each other. Okay, in relation to the most that they can vary with each other, what do you think that is? Standard deviation of what? It's the denominator. That's right. So the denominator represents the most that the covariance could be. So the covariance for linear relationships is maximized when all of the pairs fall on a straight line. So here we have this like straight line, right? All of our dots fell right on the straight line. Now think about that. When all of the things vary together perfectly, covariance should be maximized. They are varying together perfectly. It's like falling on a straight line. If they're not varying together perfectly, then you have things falling off of that line. Some might fall on it, but some fall off of it as well, right? So, in our earlier example, we had data like this. All of the pairs fell on a line, a straight line, with, I guess that's sort of redundant, on a line with a positive slope. So, let's see what would happen if they didn't. So this is what we had before. These were our data, these were our differences, these were the standard deviations that we calculated, which will be important because we wanted them here. And we had our covariance, which was 2. And notice, covariance, 2, SD1, so the standard deviation of, I guess that should be SDX and SDY. Does that? They equal each other. 2 equals 1 times 2. Okay. I said that you should have the covariance being maximum in that situation, and it should equal that. So that should be the maximum. So let's do a different example and see if variations affect it. So let's do another straight line, but let's change the slope. So before we had 1, 2, 3, 8, 4, 6, 8. Now we have 1, 2, 3, 8, 6, 4. So 8, this point is the same, 6, 4. So now we have a line that looks like that, right?
Negative correlation.
There'd be a negative correlation. Oh, we
Minus
haven't
1.
gotten to the correlation yet. We're just looking at the maximums. No, minus 1. These are brilliant. What are the differences here?
Minus 1, 0, 1.
Minus 1, 0, 1. Same thing they were doing for the first part.
2, 0, minus
2, 0, minus 2. So you put the sign for those two, and you got the differences. What are the standard deviations?
1 and 2, 3 again.
1 and 2. It's exactly the same thing that it was before. So 1 and 2. What's the covariance?
2.
How did we figure this out before?
Okay, so now it's going to be minus 1 multiplied.
Minus 1, here it is, minus 1 times,
2.
so that's minus 2 plus
0.
0
Minus 2.
minus 2.
Two.
2. Negative 4 over 2
Minus two.
minus 2. Here we had 2, there we had minus 2. Now, when we had everything falling on a straight line with a positive slope, I said that that would be our maximum. Now we have everything in a straight line with a negative slope, but this is going to be our minimum. And so the covariance, which was negative 2, if SD1 times SD2 was our maximum, then SD1 times SD2, take the negative of that, should be our minimum, right? And this, so this was negative 2. SD1 times SD2, that's 2, minus that. Minus 2 equals minus 2, which is less than 2, right? Minus 2 is less than 2. Okay?
You mean the SD1 for the first one or what?
I mean x, d, x, and y. This and this. Because in our formula, I said this is going to be the most that the covariance should be. So I'm comparing it to that. Okay. What if we compared it to something that wasn't a straight line? So this is our first straight line. Everything's the same as before.
It will be between -1 and +1.
It will be between -1 and +1. Okay, that's a prediction. Maybe, maybe not. We'll see. So the data, 1, 2, 3, 8, 4, 6. So we need to calculate the means. They're the same, right?
Yeah.
So what are the differences?
First one is the
First one is negative 101.
minus
Okay, 2
2 minus 2 0.
2 minus 2, 0, right? What are our standard deviations?
Same.
Exactly the same thing. We're working with exactly the same numbers. Okay, our covariance, what is that?
So -1
Minus.
minus
-1
-2.
0 and 0.
Does everyone see how I'm getting this? We are multiplying the first thing here, -1 times 2. Then we're multiplying the second thing with this second thing. Good grief. And we're getting that. And then we've got the third one to come up with this, right?
Divide by 2 times 1.
Divide by 2. Okay, so we have -2 divided by 2.
Minus 1.
-1. Yes, perfect.
Between 8 minus 1.
This is between
-2
-2
and 2.
and 2, right? So you said it would be between
No.
1 and -1?
Correlation.
The correlation should be between 1 and -1, but we haven't got there yet. You're absolutely right. Okay, let's do a correlation. So this is the information we already have. We have the data, we have our standard deviations, we have our covariance. So what's the correlation here?
1.
-1/2.
-1/2, so it's -0.5.
In this note, it's 1.
And this is 1.
2 minus 1, 2.
So I think you were working for the last example. Here, covariance is 2, so we have 2 over 1 times 2.
So it's 1.
So 2 over 2 is 1, which is exactly what she said earlier. It's a perfect correlation. It should be 1. All right, that was super easy. Let's do another example for our second one that we talked about.
Minus.
On the line, but in the same way, -1? How are you doing this so fast? Okay, I gotta do the calculation because I'm just not that clever. -2 over 1 times 2,
Perfect
-2 over 2, -1. It's perfect negative correlation. Beautiful. So easy. Let's do the third example. Okay,
minus 0.2.
so we have -1 over 2 Negative 0.5, so this is the one that you were solving before. That's exactly right. So this is between, as she said, it's between 1 and negative 1, the correlation. The covariance wasn't, but the correlation is. Okay, easy. Let's do one more. A new example. We have 1, 2, 3, and 5, 8, 5. What is the mean for the first part? 2, that's easy. What's the mean for the second? 6, 9, 6 point something? It's 6. 5 plus 5 is 10. Plus 8, it's 18. Divided by 3, that's 6. So 2 and 6. Don't feel embarrassed. I mess up simple stuff like this on YouTube. Hello, everybody. Okay, so what are the differences?
First one is same.
First one's the same.
Others is minus 1. So positive 1. I minus 1.
So the first one's the same that we had before. The second was minus 1 to minus 1. If we were to plot this, so we have 1, 2, 3, 5, 8, 5. So this was 8. So that was for the middle one. 7, 6, 5. So we have something like this, right? Okay. What are the standard deviations?
1.
1 for the first one. The second one we're going to need to compute. So square this. 1 plus 4 plus 1 equals 6 over, we need to subtract or divide by
Degrees of freedom.
degrees of freedom. 2, 3.
Square.
Okay, square root of 3. There you go. So 1 and square root of 3. So what's our covariance?
1 plus 0.
1 plus 0. So minus 1 times minus 1 is 1 plus 0 times 2 is 0 plus 1 times minus 1 is minus 1.
0.
0.
No correlation.
We're not done yet. We need to divide by 2. There's no covariance. I'm not as smart as you. I'm going to have to calculate the correlation.
Yeah, you should.
How do you know that?
Because it's basically
But
go to
it's
0 over 1 multiplied by
Yeah,
x.
standard
It's still
deviation.
So the formula, we're going to have 0 on the top, right? And the only way we're not going to have 0 is if this is also 0. Which, depending on how you deal with that, is either infinity or not defined. Okay, but this is not 0. It's 1 times square root of 3. So we have 0 over the square root of 3, which is just 0. Oh man, it's so easy. Okay, so R, this R thing, this is known as the correlation coefficient. And I said basically it's a measure of how much the variables vary together compared to how much they could maximally vary together, right? And what this is telling us is it's a measure of the strength and the direction of a linear relationship, right? It was strongest when we had something on a straight line. If we don't have something exactly on a straight line, we won't get a perfect correlation. Unless we're fitting some other type of data. What's funny? My fly? Okay. So, I meant to ask what measures the strength. The absolute value indicates the strength of the correlation or the strength of the relationship between the two variables. So things like 1 and -1, the maximum and the minimum correlation that you can have, they're both equally strong. They both fell on a straight line. The variance in one perfectly described the variance in the other. It's a perfect relationship. Perfect. You know, unfortunately, with marriages and friendships, There are no perfect relationships. You have a bit of variations beyond the nice straight line. But that makes life fun. Okay, so 0 indicates no relationship. 0.48 and negative 0.48, they are equally strong. How strong are they compared to 1 and negative 1?
Less.
They're not as strong, right? So these, even though they have different signs, they're both equally strong. This is stronger. 0.49 would be stronger. Negative 0.53 would be stronger. It's the absolute value that matters when you're talking about the strength. This is an imperfect relationship. So we have a perfect relationship on one hand, no relationship for 0, and imperfect relationships all the other times. Yes?
How strong is it should be to consider it as significant?
That's an excellent question. So previously, when we were doing tests, we said, you know, you are almost never going to get the true population mean. And we had to create this sampling distribution of the means, right? And he has jumped the gun. We are not even going to talk about this today. But we will be talking about it soon, because he's absolutely right. What determines whether or not something is strong enough? So the null hypothesis would be that rho is equal to 0. Or you could maybe make a specific alternative. Rho is equal to negative 0.2. Right? And you are going to test that. What do you think the test is going to be based on? It's going to be based on the size of the correlation that you observe. It's also going to be based on degrees of freedom. Yes. Yeah. So we will come back to this and look at the hypothesis testing for this soon. All right. So the correlation coefficient, I said it measures the strength and the direction of a linear relationship. So the absolute value indicated the strength. What indicates the direction?
Signs. Well, it's positive, it's
The sign. So the sign. So if it's positive, like 0.3, 0.72, 1, this means what?
Positive.
We have a positive correlation, which means what?
As the first increase and the second increase.
Yeah, as one thing increases, the other thing also increases. We can say the opposite of this too. As one thing decreases, the other decreases too. Right? So with a positive correlation, increases and decreases in one are associated with the same type of change in the other. They both go up or they both go down. Okay? This is like our first example. If it's negative, negative 0.18, negative 0.63, negative 1, we have a...
one decrease, one increase. One of them increasing and the other is decreasing.
Yeah, this is a negative correlation. And what happens is that when you increase one thing, you decrease the other. The more children you have, the less free time you have. The more children you have, the less money you have. That would be an example, 2 examples of negative correlation. This is like examples 2 and 3. Okay, before we said that when variables vary independently, they were not correlated. You guys remember that a little bit? It might be tempting to say the opposite. Well, if there's no correlation, they must be independent. Don't do this. Don't do this. For curved linear relationships, imagine we have something like this.
There's no correlation, but they are not independent.
Yeah, y absolutely depends on x. Here we have a perfect curved linear function. One thing completely depends on the other. However, if we try to fit a straight line to this, like which straight line goes best, there's no correlation. So when you go up in one, okay, we're going up in one here, We're going up in one here. Oh, but over here we're going up in one, and we're going down in the other. Right? Okay. We may see how to account for these types of relationships later. Okay. Correlation and causation. I think this is my last slide, hopefully. So correlation does not mean causation. I believe I said this in intro, and I'm saying it again here. And in every statistics class you take, probably except for advanced graduate statistics, you will hear this. Yeah.
In details and level, we could have just indicate causation, right?
With t-tests and ANOVAs, not necessarily. So, there's a difference between like correlational research and experimental research. With the experimental research, where the experimenter manipulates something and it has done a good job controlling everything else so there are no confounds, then when you find those two things to be different, based on your manipulation, then you have really strong evidence of a causal relationship. However, you can test things using a t-test. Is there a difference between males and females in driving ability? You can do this with the t-test. But just because you find that men stink driving and women are so much better, that doesn't mean that it's anything wrong with men inherently. It could be something else, right? It could be society telling us that we have to be bad drivers or we aren't going to fit in the club. So we all really could be excellent drivers if we wanted to. We just choose not to fit in with the group. All right, so it might be tempting to say that since X and Y are correlated, one thing causes change in another. Don't do that. Something else might be causing changes in both. If you didn't have my intro psych class, I like to talk about ice cream and drownings. These are both positively correlated. Ice cream sales goes up, drownings go up. Does this mean we should ban ice cream sales? No. We need to ban summer. Don't ban summer. When the temperature increases, people are hot, they want something cool. Ice cream is cool. When the temperature increases, people are hot, they want to get cool. They turn on air conditioning, they jump in swimming pools. You don't drown very often if you aren't in fairly deep water. You don't drown in your shower unless something really bizarre happens. Okay, so next class. I'm not positive that we're going to do regression on Monday. We may be doing, this is for the next regular class. So for the stats lab, I'm not sure if we're going to get into the hypothesis testing then. If we don't, then we'll be doing that on Monday.